Research is hard. Probably everyone watching right now experienced this at some point, and this series of videos is intended to make following recent research in the world of vector addition systems even just that slight bit easier. This video specifically is the last in my series about the GVAS reachability problem. The video should be watched in sequence. In particular, in this video, we assume that parts 1 through 4 have been watched. With that out of the way, let's finally take that last hurdle. Okay, so GVAS reachability explained. The final stretch. So let's first repeat where we are standing. So the situation is actually quite simple to describe at this point. Last time we defined the function forward ideal, and we showed that assuming this function is computable, we have a full algorithm at this point. Every single class, almost linear, thin top branching, has a sufficient condition. The pumping cycle is decidable. There is a decomposition procedure, and the same for different cycle. Decidable, and we have a decomposition procedure that decreases the rank. So this is the top 3 rows. Hence for today there is exactly one thing on the agenda. And like you can probably feel from my enthusiasm, like this is the part that we felt like we had to put the most work in, and at this point it's the nicest part of the whole algorithm. So how do we compute forward ideal? The last puzzle pieces. Okay, so I will today start with some overview. Well, the table of contents kind of spoilers the overview a little bit, but I nevertheless think a table of contents is useful. So we're going to compute minimal self-covering configurations. We're going to show that forward ideal is computable if some counter is large. So we're going to do some kind of Rackoff argument. Then we're going to define what a reduced flow tree is, and we're going to use them to compute forward ideal for an arbitrary input. At which point, as I already said, the GVAS reachability algorithm will be complete. So, forward ideal, how to compute it, the overview. Okay, the basic is it's a horrible proof by induction. But let's first restate what was even forward ideal. So, we defined what the reachability set is. This is all the vectors t that are reachable. But as always, I put here the reminder that if A has some source and target attached to it, then this rel of A, this intersects with the corresponding source and target. Like I don't write it because for me this is just the definition of rel of A, that it contains this. But I always like to remind the reader of this because you might forget this at some point, and this is one of the reasons why computing forward ideal is difficult. And so what is forward ideal? Well, we have now defined the reachability set, and then once we define the reachability set, we can downward close it, and we can consider its set of ideals. So the downward closure always is the finite union of ideals, and we want to compute this. Okay, so let's start with the overview, and this is really the most important part. I'm trying to not be too fast here, even though I'm very excited, because this is the point that needs to be understood very well in order for you to understand now the rest. This can be the most beautiful part of the whole algorithm or the most ugly, depending on how well you now manage to listen to me for the next 2 minutes. So, we compute forward ideal by induction on the following pair. We take the nesting depth of the grammar. This is a concept I defined last time. Well, the main thing you have to know is that if you take if you're the top branching and you take an SEC below it, then this has a lower nesting depth. This is almost the only thing you need to know, if not the only thing. Like, that's why I'm not going to repeat this definition now. That's the one thing. And well, the other thing you have to know is that this is the rank of our procedure. So this is the rank of our reachability algorithm. And then secondly, the second part is the number of counters. So this, we consider this as being lexicographically ordered. So the nesting depth is more important, and then the number of counters is less important. Okay, so example. If you have nesting depth 5 and you have 7 counters, and the other thing has nesting depth 4 and it has 10 counters, then the first is larger than the second. Because you take lexicographic ordering, first you count the nesting depth, then you count the number of counters. On the other hand, if you have the same nesting depth but you decrease the number of counters, then of course you also become smaller. So for a nesting depth 4 and 10 counters is bigger than nesting depth 4 and 9 counters. And this is the main mechanism we will use. We will attempt to decrease the number of counters. So when we say we compute forward ideal by induction on this pair, we really mean we compute forward ideal first assuming that our system has 0 counters, then assuming it has 1 counter, 2 counters, 3 counters, and so on. Like in the sense of we're just going to project some counters away and then we're then they will re-emerge. Okay, and then secondly, why do we put the first part into the induction? So this was one of our main ways to compute forward ideal. Now, actually, the only way to compute forward ideal is if you have some non-terminal and it is a s goes to t omega and this fulfills the sufficient condition. Remember, perfect means fulfills sufficient condition. If this fulfills the sufficient condition, then forward ideal is just the set with t omega. And then I don't write the set brackets. And why is this? So by definition, remember rel of A intersects with t omega. Because rel of A intersects with t omega, it is trivial that forward ideal, that the downward closure of the reachability set, that this reachability set is contained in the downward closure of t omega. This is straight. In fact, it is contained in t omega. This is straightforward. The question is why is the opposite true for the downward closure? So why is the downward closure of the reachability set equal to the downward closure of t omega? And the answer is, well, this is where you use the perfectness condition to show that for anything in t omega, actually if you just make it a little bit larger, then you can ensure that this becomes a run. We're not going to do the argument here, but this follows either from asymptotic over approximation or kind of you can just feel this. The point is that the definition of the sufficient condition exactly tells you if you add your different periods often enough, then you actually get a run. And so this guarantees you this downward closure condition. Okay, so this is why if you can decompose into things fulfilling the sufficient condition, then you can compute forward ideal. In particular, this means forward ideal of S and A is computable for all non-top SCC non-terminals. So anything that is not in the top SCC is harmless for us. The only thing we have to care about are the top SCC non-terminals. The lower ones we can essentially immediately kill by just applying forward ideal. Okay, now how do we deal with top non-terminals? Well, let's start with what's the general structure of the argument. Okay, so what do we have to do? Well, we want to prove it by induction. So, well, we have to prove an induction step. We have to go from d to d plus 1. Should be I just try to state the obvious, right? We have to prove an induction step going from d to d plus 1 counters. I guess there is also an induction step where you increase the nesting depth and you go to 0 counters. But if you have 0 counters, then forward ideal is trivial. Right? So if you have 0 counters, then you just ask whether you can derive anything. You don't have a counter, you're just a push-down automaton. the only question is, can you derive something, and this is trivial, right? So 0 counters is not a problem. The question is what, and so the only interesting induction step is how do you go from D to D plus 1 counters, right? This is the only interesting induction step. And this is what I will now describe to you. Okay, so we assume that for our current nesting depth and D counters we can compute forward ideal. And now our argument will be as follows. From this, it will follow that we can compute the set of minimal configurations which are self-covering. This essentially means they have a pumping cycle, but like I don't always want to say a configuration having a pumping cycle, so we give this a more like catchy name, and the catchy name for this in the literature is called self-covering. But really this just means has a pumping cycle. And so we claim that if you can compute forward ideal for some given number of counters, then you can compute the set of minimal configurations which are self-covering for the same number of counters. Okay, now this is where it gets interesting. We claim that if you can compute the set of minimal configurations which are self-covering with D counters, then you can compute forward ideals for D plus 1 counters. But under the assumption that one of the counters is very large. Okay, so this will be the step where we will go from D to D plus 1 counters. The magical step is if you can compute the minimal self-covering configurations, then you can now add one counter, but as long as that one is large, you can still compute forward ideal. And well, the idea for this is some kind of Rackoff. Like if you want to compare this to normal VASS, it would be some kind of Rackoff step. A large counter can essentially be ignored. And then, assuming that it's computed for large, well, you probably guessed it, but now we're going to compute it for arbitrary configurations by just using some kind of exhaustive search argument. Okay, so this is essentially the 3 steps we need to do. Forward ideal compute. So I already explained to you that this is a D goes to D plus 1 is the only interesting induction step. D goes to D plus 1, only interesting induction step. And then, if this is the only interesting induction step, how do we prove it? Well, this. D goes to D plus 1 by D goes to computing minimal self-covering configurations, jumps to D plus 1, but assuming a counter is large, jumps to arbitrary D plus 1 by exhaustive search. This is the structure we have concocted for how to compute this. It's a genius structure. Like at this point, the proof is way simpler than the original. Genius structure we have concocted here. But okay, I hope you have at this point understood how we're going to do it. So now let's dive into part 1. If forward ideal is computable for D counters, why can we compute a set of minimal self-covering configurations? Okay, so let's start with self-covering configurations. So a triple SAT is, well, this is in the literature usually called diagonal self-covering, but since I won't be using the other version of self-covering, this is just self-covering for me. SAT is self-covering if you can reach some S prime AT prime where, well, you have increased all the counters. Well, and by all the counters, I mean, of course, everything that is like non-rigid, etc., right? So all the J's that are not in, like, not rigid, not rigid, and not omega. Well, actually, when we do this, we just assume there are no rigid counters. Yeah. The interesting thing is the number of counters that are not omega. Okay. So this was self-covering. Now we're defining the set of configurations which are self-covering. Obvious. And well, we make an observation. So again, this is not a complicated observation, but this set is upward closed. If you have a derivation that pumps you, then this derivation is also enabled at every larger location. Well, when I say larger location, of course, this kind of like talks about rigidity and so on. Like there's some non-triviality involved. Like forget about the stupidities with rigid, etc. Like I'm trying to leave this as simple as possible. Just imagine that like you have normal counters. No, there is no stupidity and no stupid omegas. Like imagine that the starting vectors are normal vectors and like you want to like get to vectors that have like kind of an omega. Really, this is I am really trying to keep this simple here in this description. Then it's up or closed. If you have the stupid rigidity to worry with, then you have to worry about the fact that your B's have these conditions attached to them, right? S goes to T, which causes some counters to be like not monotone. Like forget it. It's essential. Like forget about those counters. It's really a stupidity. Forget about the rigid counters. They are stupid. Okay. Okay. And now the lemma is, so this was as I said before, we claim that for if we have less than D counters, then U is computable. And so again, like for the ones who don't like to ignore the rigid counters, less than or equal to D counters means of course counters that are non-rigid but not omega. Okay, but again, imagine that there is no rigid counter. This is a stupidity. This is the ones where you are not monotone, but on your SEC they really don't matter at all. I mean, the counter is rigid at your SEC, so you anyways cannot change it. So forget it. And uh, the non-omega, yeah, I mean the omegas you can just project away, right? So again, don't care about those. You can really think that you have normal configurations. Okay, how do we compute U? Well, the idea is the following. So we have seen in the last video that assuming that forward ideal is computable, we can decide whether a configuration has a pump or whether a configuration is self-covering. So now, of course, we're going to use this. Using that construction, we know that because forward ideal is computable for less than or equal to D counters, we can decide membership if we have less than or equal to D counters. Membership in U, I mean. Okay, so we can decide membership in the set U, assuming that we have at most D counters. This will, of course, be one of our major things in order to compute U. Okay, so now how does this help us? Well, this helps us due to a result of Falk and Janssen from 1985. So if, and this is of course the one if you can decide for the given upward closed set and an arbitrary omega configuration, so this is an arbitrary omega marking. If you can decide for your given upward closed set and an arbitrary omega marking whether this is non-empty, then you can compute U, or equivalently you can compute its minimal elements. Why is that? Well, you do the most stupid algorithm you can imagine. You guess the minimal elements. Okay, call this set minimal elements M. And now what do you check? Well, we have to check that M upward closure equals U. What does this mean? Well, this means we have to do two checks. We have to check that M is included in U. Here we do membership tests, right? Like, in particular, this condition means membership tests are possible, right? So we do membership tests. And the other thing we need to do is we need to do U included in M upward closure, or equivalently, we need to show that, we write this differently. We write U intersected with the complement of M upward closure is empty. And now the complement of M upward closure is a downward closed set. This is a downward closed set D. So we can write this downward closed set as a union of omega markings. I think at this point, yeah, at this point you would not be able to see it anymore. So we write this as union I from 1 to R S omega I. And now for every one of these, we check whether the intersection is indeed empty. And this we can do by the assumption that we can check this, do this emptiness test. So in particular, you see that we actually need the condition that this is omega markings, and we need to check emptiness and not just membership. Membership alone is not enough. We need to be able to test also intersection with downward closed sets. Okay, so this means we have to check that this here is decidable, right? If we can show that this here is decidable, then we can compute our minimal elements. So how do we do this? Well, we can check membership. So the only problem is what do we do with omegas, right? Well, here we're going to do a little bit of Z pumps and lifting, and this will feel very much like Rackoff. So we're now defining when a configuration is Z self-covering. Well, you have like essentially the same, but you want to only have a Z run that goes and increases you. And well, whether you have a Z run that increases you does not actually depend on your source counter values. I mean, you're allowed to go negative, so you can start at 0 or wherever. You anyways have the same pump. And you can decide this using an ILP. Well, I'm not going to write the ILP. It's actually not 100% trivial because you need to think about like producing non-termers on the left of your A and on the right of your A is a bit different. So it's not completely trivial, but you can just do this with an ILP. And of course then, if we don't have a Z pump, then clearly there is no pump. So from now on, we assume that there is a Z pump. And now here comes the clever lifting lemma. Assume that you have a Z pump. Then the condition we want to decide whether U intersected with some such omega triple is empty. This is equivalent to checking whether the triple where I project away the omegas is in U. So for example, let's say I want to check whether U intersected with omega 1 A omega 2, whether this is empty. Well, this condition tells me that this is equivalent to checking whether 1A2 is an element of U. Well, U with accordingly the smaller set of counters, right? Yeah. So whether this new configuration here has a self pump. And now the point is, we have just managed to get rid of the omegas, so now it's not an omega configuration anymore. This is just a membership query. So assuming we have this lemma, we can in fact check whether we can in fact compute the minimal elements of U via the Falk-Janssen argument. Okay, so how do we prove this? Well, and first of all, why is this not trivial? Well, think about what it means with this self-covering thing. So what does the first condition mean? The first condition, this is non-empty, means that there is some large number, say for example, that there is some large triple, say 10,000, 1A, and then 11,002, which is self-covering. Okay, so here we have large numbers and we have to be self-covering. And the other thing, well, is just 1A2 needs to be self-covering. What's the difference? Well, a very important difference is, I mean, you are allowed to start arbitrarily high here, like it was omega, right? You are allowed to start arbitrarily high, but this counter needs to be pumped. This counter is allowed to start at a high value, but the pump that you use has to actually increase this counter. While self-covering in this configuration here does not increase this counter. Self-covering in this new configuration, 1A2, just means it pumps the second counter. The first counter is completely ignored in this new membership query. Okay, so this is the major difference between these two. The second one allows you to like completely ignore your omega counter, so it doesn't need to be pumped. The first thing needs it to be pumped. Okay, so obviously like one direction is clear. If you if this guy here, if some guy in the upper thing is self-covering, then you have the lower thing. So one direction that is obvious is the if direction. Like this direction is obvious. So why does the other direction hold? Well, I will actually just tell you essentially what the number is, and you will immediately see why. Okay, say this 1A2 has a pump of size, like 1A2 goes to 2A3, and this derivation here has, say, size 10,000 or something. Okay, so this derivation has some size and like, so some minimal number that occurs in this derivation. Say the minimal number that occurs in this derivation, like the effect on the omega count is like minus 10,000 or something. Okay, like how many productions does this use? Something like this, some size. And well, we're also looking at what is the size of the Z pump. Remember, we assumed that there is a Z pump. So let's take the Z pump for this guy. Let's take the Z pump for omega 1A, omega 2. So the Z pump starts with 0, 0, A. Like, remember, the Z pump does not depend on where the starting values are. Starts here, and then over Z, it goes to 1, 1, A, 1, 1. Okay, and let's say this Z pump has size 5,000. Like, the numbers are just an example. You can obviously make this work with whatever numbers. Okay, now what do? Well, we are going to as number here for the large thing. We're not going to put 10,000, but we are going to put it was 10,000 plus 1 times 5,000 plus 1. Okay, and why this number? Why this number? Well, think about it as follows. What are we now going to do? Okay. So, at the start, the problem is that the Z pump is not usable. So this size 5,000 means that essentially this Z pump implies that if I were at 5,000, then I could apply it, right? So 5,000, 5,000. Say this has an 5,000, 5,000, a 5,000, 5,000. This has an actual pump. This is in U. Like the Z pump at some point becomes an actual pump. Say at 5,000, like some large value. And now what we're going to do is we're going to use the pump for the thing that is not omega. We're going to use this pump here that we have by assumption. We're going to use this pump 5,000 times. What happens if we use this 5,000 times? Well, once we use it 5,000 times, we know that at that point, this counter here is greater than 5,000. So this counter is greater than 5,000 on both sides. Okay, just because we applied it that often. Okay, now what happened with the other counter? Well, this is why I chose the number the way I did. I chose exactly the product of the two sizes. So for 5,000 times applying this, if I 5,000 times apply something of size 10,000, then this means my counter is at most decreased by 10,000 times 5,000. So this means this large counter still has how much value in it? Well, 10,000 plus 5,000. Importantly, it is still greater than or equal to 5,000. So this means it can still apply the Z pump. So we have used the counter on the second, we have used the pump on the second counter so often that the second counter can now be pumped. And the first counter was so ridiculously large that even after doing it, the first counter is still ridiculously large. And this means that now both of them are large and we just use the Z pump ridiculously often. Namely, how often do we repeat the Z pump? Well, we repeat the Z pump 10,000 plus 1 times 5,000 plus 1 times to make sure that we have re-added all the value that we have lost. So this is the proof of the other direction. With this, we see that these two conditions are in fact equivalent, and hence we can decide this intersection non-emptiness by just calling membership queries. Okay, so how does this allow us to jump to d plus 1 counters? Right, so we now have this, and we want to prove that there is, so this is the formal specification of this large. So we claim that there is some number such that for all triples with less than or equal to d plus 1 counters, and at least one counter is large on both sides, so at least one counter is large in S and a not possibly different counter, this is possibly different, this is actually important, possibly different. So some counter is large in S and some possibly different counter is large in T, and we have at most d plus 1 counters, then we claim that S, A, T, and U is decidable. So, how do we do this? Well, actually the idea is already what you have seen here. Because there is now one trick, this membership query here that we reduced to, it uses fewer counters. This membership query, if I have one counter as large in the input and large in the output, uses fewer users in fact fewer counters. So what we're now going to do is similar to what we did before. What is the proof? Well, I will just define to you the number and then you can go through last slide to see that it actually works. So we compute the set of minimal configurations. Compute minimal configurations of U assuming some counter is ignored. Okay, call this set of minimal configurations, call this M. Now for all M there is some pumping derivation rho M. And well, we assume that there is a Z pump, otherwise we know that, like, otherwise it in U is decidable because we just decide that there is no Z pump. So assume that there is a Z pump, a rho Z. And now we define B as follows. B is defined as the maximum over all M in M, rho M, like size of rho M, times the size of rho Z. And of course I made again the stupid error, like has to be a plus 1 here. I don't quite remember where this was needed in the proof, but this is needed. We need a plus 1 here on both sides. Okay, but this is the definition of B. And now if on both sides some counter is above this, then well, this is the counter that you ignore, and then you can decide whether this is in U, well, by using the corresponding pump for the corresponding pump that you actually already computed when you ignored a counter and computed M. Yeah, so this is how this is done. Okay, so let's again move the lemma that we now have to the right-hand side. So now we have a lemma that tells us that if you have d plus 1 counters, this was the important jump to d plus 1 counters. If you have d plus 1 counters and, well, some counter is large in the input and in the output, then you can decide membership in U. Okay, but what we actually want to do is the following, right? We want to bound B prime such that for all SA with at most d plus 1 counters, and, well, one of these counters is large, we want to compute forward ID. Okay, so how do we do this? Well, there is again a genius technique that a mad genius of Ehren has struck again. We take the following. Okay, so we take the set of minimal homogeneous solutions of Z reachability. So we can think of Z reachability as being some kind of ILP. And then, well, it has some homogeneous versions, and we consider all minimal homogeneous solutions of this. This is a finite set, we can compute it, no problem. And now what do? Well, we define B prime as, well, I simplified slightly. There is of course also something for the inhomogeneous solution. Forget it. The main part is this. You take the bound B that is guaranteed by the lemma on the right hand side, and you take times the maximum of the norm of one of these minimal solutions. And now what is the point, right? I mean, why would you do this? Well, take some vector S where some counter is greater than B prime. So we have S of I is greater than B times the maximum over all H in H, norm of H. Okay, and now what do? Well, we want to compute forward ideal. How do we do it? Well, consider the, well, we're going to compute the Z reachability set. Well, we can define this in the same way as the normal reachability set. And then we can consider its downward closure. Let's compute this. It's a Z reachability set, so this is easy to compute. And let's write it as a union of ideals. Union I from 1 to R, S omega I, or T omega I. Okay, now here comes the mad genius. Okay, so there are two cases. If T omega I contains omega, well, omega is greater than B. Yeah, so I should say what we want to prove. Well, what we want is essentially we want to create a pair SA T omega I, but we want this pair such that this T omega I has some large counter. And now, well, there are two reasons why it has a large counter. So, because we want to apply the right lemma, right? We need to get into a situation where both sides have a large counter, not just the input. Okay, there can be two reasons why this has a large counter. Okay, so one reason is that this might contain omega. If this contains omega, well, omega is in particular greater than B, so there is a large counter. So let's look at the simpler case. Let's look at the other case, not the simpler case, the harder case. This does not contain omega. Okay. Now this does not contain omega. So in fact, this is actually a normal vector. So we have SATI. Okay, what do? Well, we considered here the Z reachability set. So this Ti, well, this Ti is some Z reachable vector, some maximal Z reachable vector. So Ti is a maximal Z reachable vector. Okay, but now comes the trick. We started here with S, and S had some counter that was ridiculously large. S had a counter that was larger than B many homogeneous solutions. So this means when we write the pair STI as a sum of homogeneous solutions, as a sum J from 1 to some S Hij of homogeneous solutions, well, we must have S is greater than B prime. S is greater than B. Why? Well, because S, oh, I shouldn't call this S. S was like the worst naming I could have done. M. Let's call this M. Okay, we must have M is greater than B. Why? Well, this sum of homogeneous solution of, well, minimal homogeneous solutions must equal STI. In particular, it must equal S. But S has a ridiculously large counter. S has a counter that is larger than B times the max norm of one of these guys. So simply by like pigeonhole principle, we know that M is larger than B. Okay, I forgot one more part. I have to do times D. Times D plus 1 times the number of counters. This will now become 1. So this M is in fact not just larger than B, it's larger than B times D plus 1. Okay, now we will see where this goes. Okay, but these homogeneous solutions, they must also contribute to Ti. Every one of these must contribute to Ti. Why? Well, remember that we want something maximal Z reachable. If one of these TIs, if one of these HJs goes and says, well, I start with some vector x and this vector Z reaches 0, if this is what HJ does, then we can just remove this HJ, like we remove it, and we can replace it with monotonicity. We can just leave x lying around and leave x at the end. And we reach a larger vector. So it cannot be the case that Hj does not contribute to the output. So Hj must contribute to some counter. Okay, so it must contribute to some counter. Well, there are only D plus 1 many counters. There are only D plus 1 many counters. It contributes to one of them. So this means at least B plus 1 many HJs contribute to the same counter. But this now means that the corresponding counter, well, this counter is greater than B in Ti. It's like it's a magical mechanism. This is so you know that in fact there is a large counter. Okay, now you might ask yourself, okay, how in hell did this now help me? All I now did was I computed the maximal Z reachable vectors, and okay, wonderful, I made sure that all of them have a large counter. Okay, how does this help me? Well, remember that whenever we can decompose something into perfect parts, whenever we can compute, if we can decompose into perfect parts, then this implies that forward ID is computable. So what we are now going to do is we're going to do exactly this. We are going to decompose into perfect parts. How do we do this? Well, so remember that the TIs were the maximal Z reachable vectors. So it's enough to consider all the triples SATI and compute the reachable part inside TI. Compute reachable part in TI. In TI for all I. Okay, so we have to compute the reachable part in all TIs. Now how do we do this? Well, remember that both S and TI have a large counter. So this means that by the lemma on the right, we can decide pump. We can decide self-covering. This in total actually means we can decide the sufficient condition. We can decide the sufficient condition for reachability. We can decide the sufficient condition for reachability. And not only that, but I did not write it here, but here we can decompose. And this is now going to become important. Because now what do we do? Well, we can decide the sufficient condition for reachability and decompose. So what do? Well, we decompose. We decompose into smaller nesting depth. And now what does this mean? Well, this means we can decompose into perfect by induction. We can decompose into perfect by induction. So this means we can decompose SATI into perfect, guys, and therefore compute the reachable part in TI. And this in particular means we can now compute forward ID. We can piece together forward ID from the different parts. Or, well, there's one more case. I just said here we decompose into smaller guys. Well, there's one more case. What if we are perfect, right? So there is one more case. If perfect, then actually we can just output a TI as this for this corresponding part, because then TI is actually also n-reachable. So like this was one of the lemmas I showed earlier at some point, like very early on. If something AS goes to T omega is perfect, then in fact we know that forward ideal equals this T omega. And this is what we're now doing. If the sufficient condition does not lead to decomposition, but it actually holds, then we can just output Ti. The maximal Z reachable vector is in fact also a maximal N reachable vector. And so hereby we have managed to compute forward ideal, assuming that some counter is larger than B prime. I know that this proof took a few steps. It was not easy, but now we have finally managed to jump from deciding self-covering to computing forward ideal. And at this point, we can finally be excited and go to the last step, the last minor step. We have to now do exhaustive search to compute forward ideal also for small inputs. So let's again put on the side the lemma that we now have. We know that there is some number such that if you have d+1 counters and one of them is large, then we can compute forward ideal. And now what are we going to do? Well, as I said, exhaustive search. So what we're doing is we define small configurations as those that where every single counter is in the interval 0 to B prime, and large configurations, L, as the opposite, where either some counter is omega or some counter is large. And now intuitively what we're going to define are like derivation trees that are labeled with triples. So imagine you have a derivation tree A, and then you go here to, like, you have a production A goes to A1, A2, A3. Then what's going to happen is here you had some input S and some output T. And now when you apply the derivation tree, well, in the derivation tree you would have children A1, A2, A3. And now what we're going to have is these are again going to be labeled with some vectors. Here is going to be some T1. Here is going to be the same T1 because like these have to match. Here is going to be T2 and here is going to be T2. And I already wrote S and T at the start because again those have to match. So we're going to define such trees. And we're going to call them flow trees, or well, reduced flow trees, because we're actually going to like try to insert omegas whenever possible. So, well, in the definition I have for simplicity not written this condition that these guys here have to match, but like I wanted to mention this physically because writing this is surprisingly annoying if you have very large children and so on. But of course we want these different configurations in this derivation tree to match. Okay, the remaining condition that we want are the following on the labels. So first of all, non-repeating along branches. So this means if you have SAT up here, and now you do something, and you do something here, and you do something here, well, you are not allowed to see SAT again here. This is not allowed. But what is allowed, and I should explicitly mention this, is that you have some configuration here, say 0, A0, and you have the same configuration as 0, A0 also here. This is allowed, just not on the same branch. Then secondly, we need that all the sources are supposed to be small. Or if the source is not small, this is if the source is large, then we want to compute forward ideal immediately. So then we want that this is a leaf. So I didn't write it, but then or leaf and well t is in forward ideal. So this means if you intuitively we're now going to construct some derivation, and sometimes something is going to grow large. So here we grow large, and then we terminate the tree here, we cut it off, and we just put here something that is in forward ideal. Of course, here we rely upon the fact that forward ideal is computable if we are not small. And then finally, if you have a situation where here you have SAT prime and here you have SAT, so you have a situation like this. So there is some derivation tree here around it. And okay, this might also not be one step, this might be many steps. If you find if you have in a branch SAT and now you have a tree above it, then actually we want that this T prime here, this T prime is supposed to be omega on this counter. Like if this T prime is greater than T, and on some counter it is in fact strictly greater than T, then on this counter it is supposed to be omega. So this is the acceleration part. We want that if you have a situation like this where you write something larger above, so you should be imagining that we're building these trees bottom up actually. If we build this bottom up and here we write something that is strictly larger, then we want that omega here. Okay, so now we have seen the definition of a reduced flow tree. So what do we do with these? Okay, what we do with these is the following. So take some height of the trees, and now we're considering all the reduced flow trees. So this is the set of reduced flow trees of height less than or equal to h. Set of reduced flow trees. So RFT stands for reduced flow tree. Reduced flow tree of height less than or equal to h. Okay, so first of all, we claim that this is finite and computable. Why is this? Well, go back to the definition. Yeah, actually I wrote it on the right. Well, what can you actually have? Well, you have derivation trees here. Derivation trees. There are only finitely many derivation trees up to a certain height. And then, okay, what can be with the outputs? Well, the outputs only have very few options. So either like because once you reach a small input, you have to write an output according to the function forward ideal. And forward ideal only has finitely many. This is finite, right? So if you have a large input, then already you only have finitely many options for what you write afterwards. And well, you cannot be small forever, because small, well, you are not allowed to repeat the long branches. If you had small values all the time, then you would, of course, at some point repeat. Yeah, so this is like the intuition of why it's not hard to show that RFTH is effect finite. And of course, it's computable. I just write down all the derivation trees, right? There is no problem. The one thing I should say is, of course, when we say this is computable, we have to check this condition here. But this condition we can check because forward ideal is for large configuration, forward ideal is computable by assumption. Okay, then the second one, this here follows by a typical WQO argument. I'm not going to go into the details, but essentially the acceleration guarantees that eventually you must have eventually you should have found an acceleration. So it's similar to building a coverability tree. Similar to how coverability trees are finite, the RFT construction is also finite. Like similar to coverability tree. Like it's a similar WQO argument. You can only introduce omegas so often, and well, otherwise you cannot have a domination because you should have introduced an omega. So by WQO arguments, this construction will be finite. Okay, now, well, 3 kind of ties into 2. I said this construction is finite, but of course I need to make sure that we can effectively construct this. So how do we do this? Well, we know that we have constructed everything if, like, eventually, like, 2 tells us that eventually we must have, eventually some height does not give us a new tree. And then 3 tells us that if a height does not give us a new tree, then we have found all of them. So this is the set of all reduced flow trees. Okay, and now the fourth condition is the one you probably waited for. You can compute the downward closure of the reachability set by looking at the outputs of reduced flow trees. Namely, the downward closure of the reachability set is exactly the downward closure of the outputs of the reduced flow trees. This is not very surprising. I mean, reduced flow trees essentially simulate every single possible derivation tree. We just accelerate them a little bit. Okay, so also this is not too hard. And now from these, we can finally reach the end. The last thing we have to prove, the induction step for forward ID. Forward ID is computable for D+1 counters. Why is this? Well, essentially the 4 conditions are constructed such that this is possible. What does the algorithm do? Well, it, in a loop for h equals 1, 2, and so on, construct RFT. RFTH. Well, then essentially 2 tells us that, well, eventually if we hit the fixed point, at this point you know that you have computed all of RFT. So once you hit the fixed point, then at the fixed point, output, well, this here, the outputs of the targets of the different reduced flow trees. Well, possibly minus some minus some duplicates or something. Okay, and this, I know it feels anticlimactic. The sad thing is the last step is not that hard anymore. It's really just exhaustive search. But nevertheless, we have to do this last step. But at this point, we are done. The last step, we have finally finished our algorithm for GVAS reachability. If you think about the mosaic, it's now fully colored in green. Not only the above parts, but now also compute forward ID is colored in. We actually have a complete algorithm for GVAS. It doesn't feel as much like it because the last step wasn't too exciting maybe. We kind of had hit the climax before and we were already on the way down. But nevertheless, this was the last piece of the mosaic. The mosaic is now done, so we have a complete algorithm. And just to summarize, well, we started with some intuition. We continued with intuition, meaning I gave this top branching sufficient condition in a simplified version. We continued with the almost linear case, a kind of baby step, some people might have thought. We improved it to get it actually for all thin GVAS. Then we assumed forward ID, but we actually managed a complete solution also for top branching. And now finally, with a little bit of an anticlimactic end, we managed to compute forward ID by finishing the induction step. And so in total, at this point, we have a GVAS reachability algorithm. I hope, even though the last step was not as exciting, you are still hyped that finally you understood this algorithm. And if you actually managed to follow me, then thank you very much for your attention. It's very much appreciated. And I should mention that there are still open questions about GVAS. Just like for VASS, the complexity of reachability is still very much a mystery, especially for small dimensions. There are also other questions, like is it actually hyper Ackermann hard? There are different questions. Is it hyper Ackermann hard or is it in Ackermann? This is for general dimension, not for small dimension. There are still a lot of questions open, and I hope I managed to get you interested in GVAS. If you are even the slightest bit interested, I would be very happy to help you a little bit and to cooperate on this. Yeah, thank you for listening, and this was the end, the last of this series of videos. I have really only hidden very small details. This was really 60 pages of crueling paper. I have of course hidden a few details, but this is essentially 60 pages worth of material that you have just listened to. So really, I cannot state it enough. If you have managed to get so far, thank you for your attention.